Good morning, everyone. We'll get started. But before I start the class, I just want to know, Monday afternoon, are you guys free for one extra class? Monday, which is 29th.
Sir, we have presentation on that day.
Yes, sir. BK Dadwal sir has
Okay.
presentation with us, sir.
What about maybe after 4 o'clock or 4:30?
Sir, navigation lab is also there that day.
Tuesday? Tuesday anytime. Tuesday afternoon, are you guys free?
Sir, means the last week is completely occupied, means all the days with afternoons to till 3 p.m.
Okay, I can conduct a class at Tuesday 3:30 then. Okay.
Means Thursday, if you can take, then it would be fine.
Thursday, anyway, we have our class at 10, right?
Means Thursday afternoon, because sir, at that time we have usually don't have any class. That's why.
Okay. Tuesday 3:30 p.m. Do you have class or not?
So means we are
Or
not sure right now. Means about the
okay.
presentation. Means that's why.
Okay. What about this afternoon? Today afternoon?
We have a class at 3 o'clock till 4:30.
Okay. Okay.
Yes, sir.
All right. So let's try for Tuesday, and maybe I'll take the Thursday class also because I think I missed quite a few classes. Anyway. Okay. Let's get started with our today.
Sir, one more thing, sir.
Yeah.
Sir, regarding the you tell that you will take a design class also, sir. When we are going to take that?
Yes. Yes. Yeah, so I was thinking because of lack of time, I'll at least do a recording of the design class and put it up in YouTube.
Okay,
That
sir.
is one option. But if some of you guys are available this afternoon, I was planning to do the recording. So
Yes.
if you guys are available, then I can kind of do it as a live class and also put it as a recording.
Sir, okay, we'll inform that if we get free earlier, then we can inform. Okay, sir.
Yeah.
Otherwise, sir,
Okay.
we
So
will
I
get.
am here in campus till around 5:15. So
Okay, sir.
even if you give me a session, let's say from 4:20 or something like that, or 4:30 to 5:15, I can quickly wrap up one session. So that's also possible.
Thank you, sir.
Okay. Right. Let me know. Maybe you can put it in the group so that I can, schedule it appropriately. All right. Okay. So let's start with this topic for today, which is common mode feedback. Now, if you kind of have a flashback of what we have done so far, we started off with the device. We tried to understand how the MOSFET devices work. And also, in addition to MOSFET devices, how do these we implement resistors, capacitors, and so on. And we talked about variation, mismatch, PVT variation. We looked at single stage amplifiers, and then we moved to differential amplifiers. We looked at different op amp topologies, and we looked at we analyzed and also laid the foundations for doing design of different types of op amps, right? So now we also looked at the frequency response. We looked at stability, how do you compensate, and so on. Now this particular problem of common mode, or rather this solution of common mode feedback, is needed for a problem which is faced by fully differential op amps. Okay, this problem is not there in single-ended op amps. It is there only in fully differential op amps. So what is that problem? Now, if you take a fully differential pi transistor OTA, let's call it as ISS, right? And so how are we planning to bias this? So if you recall, when I did the op amp, I just said that we will talk about this biasing a little later for this fully differential op amp. And the reason was this common mode feedback. Now, if you kind of say, okay, I need to bias up this transistor, sorry, M3 and M4. Now, how would we typically do? Basically, we'll say, okay, I'm going to put a current mirror. And this current mirror is going to, get the current from another source. Let us say we have a reference current which is coming in, and right, something like this. All right. So let us say this is M0, or let us say this is M0. Let's call this as M5, M6, M7. Basically, what happens is this is basically VDD, and then you have IREF flowing through your M0, which generates a certain gate to source voltage, and that current is mirrored to both M5 and M6. M5 current is mirrored to, M5 current flows through M7, and that is mirrored to M3 and M4. Now, normally, under normal circumstances, you don't see any problem with this kind of a biasing, right? But then what happens is that you will basically see, there are times, although you're mirroring the same amount of current, all right, there are certain cases, or there are, because of, let's say, some channel length modulation effect, or some process corner effects, what can happen is that the PMOS side current will not necessarily be equal to the NMOS side current. Okay. In other words, ID 3,4, which is mirrored like this, is not equal to ISS by. Now, suppose ID 3,4 is greater than ISS by 2. Now, why would this happen? I mean, this can happen to a variety of reasons, right? So, what can happen is, one is process variations. Although you're mirroring the NMOS current to the PMOS, and that is expected to mitigate the problem to some extent, but still, what can happen is that the mismatch between the source to drain voltages and also the threshold voltage mismatches, which can happen between, let us say, M7 and M3, M4. Those kinds, or localized heating, localized swing, and things like that, can result in ID3 and ID4 being less than what it is exactly supposed to be, okay, or greater than what it is supposed to be. Now, suppose ID3 and ID4 is greater than, let us say, ISS by 2, where, let us say, this is the current ISS flowing through the NMOS, and ISS by 2 flows through M1 and M2. Now, what will happen? This will result in M3 and M4 going into the triode region to bring the current equal to, let's say, ISS by 2. Let's say ISS by 2 is flowing through this one. Now, this is actually a bad thing, because we know that when M3 and M4 go into triode region, the R0 is going to collapse, and therefore your gain is going to go quite low. And not only that, if you look at this V out M and V out P, the output common mode voltage, V out common mode, nothing but, let's say, V out M plus V out P by 2 is the common mode voltage. Now, this will actually go up, right? So, if M3 and M4 have to go into triode region, the source to drain voltage reduces, which means that the common mode voltage of your output is now increasing. Now, consider the other case where, let's say, ID 3,4 is less than ISS by 2. Now, what will happen? Basically, if, let us say, this is fixed by the bottom transistor, which is M6 here, this can result in M6 going into triode region, right? Because typically, this forms the first stage, and the load that is connected to the output is basically a capacitive load, and therefore the DC current has basically nowhere else to flow. It is only that these transistors have to kind of adjust between themselves I mean, the source drain to source voltages will get adjusted among themselves such that KCL is satisfied. All right. So if ISS by 2 is greater than, let us say, ID3, ID4, then basically what you will do is kind of crunch this current source at the bottom, push it into triode, or automatically it will happen such that the current through M6 is equal to ID3 plus ID4. Now what this will result in, basically this will happen, M6 going into triode will happen if your Vout common mode basically drops. And M6 going to the triode region will basically cause your CMRR to collapse. Right? So this is a problem which actually happens in practice. So it is not possible to, it's not very easy to detect this problem in schematic or even layout simulation. You can probably, I mean, look at this problem if you try to do some mismatch and so on. But in practice, when you measure the chip, this problem of the output common mode varying a lot happens. Okay. The end result that you would observe is that the output common mode voltage varies widely. Okay. And typically this problem is seen when you have fully differential systems where the output voltage cannot be readily predicted. That is to say, so for example, if you had a resistive load, okay, now you can directly say, okay, fine, my output voltage is VDD minus ISS by 2 into RD. Now, when you can directly write an equation, then it means that your output common mode voltage is pretty well defined and you do not run into these kinds of issues. But when you have a high impedance node like this, where looking at the circuit, you cannot directly write the output common mode voltage, because how will you write the output common mode voltage here? You cannot do a hand calculation here, right? So it is a complex function of all the source to drain voltages that are there. Now that is what is called as a high impedance node, and any high impedance node in a fully differential system ends up with this problem of the output common mode voltage varying drastically, and this results in op amp gain reducing drastically. This drastic reduction of op amp gain happens because one of your transistors is basically going out of saturation. Now, here this results, so in fact, this event can be so severe that sometimes the output common mode voltage can go all the way to almost close to VDD, or it can go all the way close to ground. Okay. Now, this problem can be modeled as saying that there is a PMOS current source, which we call as IP, and there is an NMOS current source, let's call it IN. And in this particular case, you're basically trying to match the PMOS current and the NMOS current, right? Now, in practice, what is happening is that there is a IP minus IN, which is going to be there, and there is a certain output impedance here, RP and RN being the effective output impedance in the P side, effective output impedance in the N side, and therefore, when IP is greater than IN, you have a positive current flowing into this output impedance, which is nothing but, IP minus IN multiplied by, let's say, RP parallel to RN. This is the output common mode voltage. So basically, when IP greater than IN, your Vout CM will basically increase, and vice versa. All right. So if there is any circuit where you, by inspection, you cannot write down the output common mode voltage by hand, and if it's a fully differential circuit, it needs a common mode feedback to stabilize the common mode voltage. All right. Now, some people might say, okay, anyway, we are putting a feedback around an op amp, right? Won't that feedback take care of it? The answer is no, because that feedback is basically a differential feedback. right? So it will only take care of the differential aspects of the system and not the common mode aspect. So you need a separate. So because of all these problems, we need what is called a common mode feedback. And this is, popularly called as CMFP, common mode feedback. Now, what is entailed in this common mode feedback? Now, any feedback, if you talk about, there are basically two things, basically two or three things, right? First is you need to sense the common mode voltage, right? Sensing of the common mode voltage is the first problem. Secondly, what you have is many times you need to have some kind of a comparison with the reference, right? What is it that you actually want? And thirdly, it is basically correction. How do you correct it? Now, first let us talk about the problem of sensing the common mode. Now, how do you think we can sense the common mode voltage of a particular differential? Now, although I have given the example of a 5 transistor OTA, this problem is there for a telescopic cascode OTA, a folded cascode OTA, or a regulated cascode OTA, all of which where you have a fully differential OTA, not the single-ended one. In the single-ended case, of course, because you have that current mirror load, automatically that will take care of all these PMOS, NMOS mismatches, and you don't have this problem in single-ended OTAs. You only have this problem in fully differential OTA. So whether it is 5 transistor or telescopic or a folded cascode, you have this problem. Now, when you are given, let us say, V out P, and let us say V out, let us say this is V out M, how will you calculate the common mode voltage, or how will you sense the common mode voltage? Now, one of the most straightforward ways to do it is basically to say, put two resistors and tap the point in the in between. Okay. So in other words, if you kind of look at this full circuit, you take the output and you take this common point. I mean, this is your differential pair, right? And what you do is at the output, you put some resistor R. So this is your V out P and this is your V out M. You put two resistors and you take the midpoint, right? Now, what happens to the midpoint of this two things? So basically, how will this sense the common mode? So let us say the V out M is basically going up like this. Okay. Correspondingly, V out P is also going down and coming like this. Now, if you do superposition, right? If you take these two waveforms, right? And if you calculate using superposition, this center node, as long as these two resistors are identical, the center node is going to be the average of the two signals, right? So when one is high, the other is low. When the other is low, the first one is high, and therefore this particular node reacts only to the common mode signal. Okay. So in fact, you can write this as, let's say, VCM plus VD by 2, and let's say the other one is VCM minus, oops.
सर डिस्कनेक्ट हो गए।
मैं वही पूछ रहा था यार, कि लाइन ही दिया ग्रुप पे भी, एकदम से आवाज आनी बंद हो गई।
Yeah, sorry guys, I got disconnected. So let me share my screen. Right. So what I was saying before I got disconnected is that if you take two signals which are like this, let's say VCM plus VD by 2 and VCM minus VD by 2, and if you do superposition, you will see that V out, let's call this node as Vx, right? So Vx will basically be equal to VCM. All right. So, but do you see any problem with this? Do you see any problem with this?
Sir, gain will
Very good.
decrease
Gain will decrease. Why will the gain decrease?
because we are driving resistors, sir.
Okay, so in other words, even if you do the so this is this center point. Let's call this point as x. It is a common mode point, which means it is a small signal differential AC ground. So if you draw the differential mode half circuit, so if you draw the differential mode half circuit, basically you have this one, and you have a resistor R2 ground, right? So if this is M1 and this is M3, now the gain becomes GM1 R01 parallel to R03 parallel to this R that you have put for sensing your common mode voltage, right? So of course, so what you will try to do in order to make this thing to reduce the impact on gain, what you can do, you basically increase the value of R. Okay. And of course, the other problem is DC. As you pointed out, you're trying to drive some resistive load. But if you try to, let's say, take this resistor to be a really high value. So for example, if let us say this is some 2K and this, let's say if you make it in such a way that this is some 5K, this is some 5K, then you have to, or even if you reduce the current and let's say these two are 10K resistors, now your R, in order not to really interfere, R should be at least some 50 to 100K, so that the parallel combination really does not affect your gain so much. Now increasing R basically has two problems. One is large area. Now, although you do have some high resistivity metal option, high resistivity material options in most CMOS processes, but still it is going to take up a large area. If you're planning to, let's say, do this, now I gave the example of a 5 transistor OTA. Now, in the case of a telescopic OTA, what happens? Now your gain, this resistor comes in parallel with what? R01 plus R02 plus GM3, R03, R02. This whole thing in parallel with this R. And therefore, this R has to be much greater than this cascode impedance value. Now, this cascode impedance value can be easily in the order of some 60, 70K, right? If you design it in a certain way. So it means that your R has to be hundreds of kilo ohms in order to make sure that you're not pulling down the gain. Or else if you put some 10K resistor, you can have a wonderful telescopic cascode, but this common mode sensing resistor itself will pull down your gain completely, right? So therefore, a large area is one major problem. And when you have a large area, you have more parasitic capacitance. More parasitic capacitance of R. Now that capacitance anyway has to be driven by what? Your poor op amp only, right? And that is going to reduce the bandwidth of your op amp as well. All right. So this is really not a good option if you are using a telescopic cascode or a folded cascode. But if it is a 5 transistor OTA, it is typically not a very bad option. I mean, you can still get away with it. But if you're using one of the cascodes, then it's a very bad option. So this results, this is basically sensing using resistors. So in order to avoid this problem, another method to sense is using source followers. So basically what you're saying here is, let us say you have this V out P and you also have V out M. Let us say this is from a telescopic cascode and you cannot afford to put such large resistors. What I'm going to do is that I'm going to take this, put it through a common drain amplifier. Okay, so common drain is basically what you put, you give it to a transistor and you take the output at the source of it, right? Okay, and here what you do is you put a resistive divider. Okay, the same kind of a thing. So basically what is happening is that, let us say this M1 source follower and let's say M2 source follower. Now these two source followers are basically going to follow the outputs V out P and V out M. And the output of the source follower, basically the source follower acts as a buffer. It is almost like a unity gain buffer, but not exactly. And the DC voltage that you are getting at these 2 points is not exactly the V out common mode. It is V out common mode minus this gate to source voltage, right? So what you would basically get at this node X is basically a kind of like you have the V out common mode minus this quantity VGS, right? But in a sense that it is going to track the output common mode voltage. It will track the output common mode voltage, but it is not exactly equal to the output common mode voltage. Okay. Now here you can put lower values of resistors because anyway you're not impacting the actual differential gain of your OTA. Now there is also one more problem. So one problem is basically that you have a kind of it's an offsetted version of the output common mode. The second problem is basically that when you have large swing, okay. So let us say if your V out P is large, the swing at V out P and V out M is quite large. Now what will happen is that let's say this is a very large output swing, right? Now what will happen is when this transistor goes really low, it can pretty much cut off your M to S, right? And M1S will be fully on. Now because of this, what will happen? This transistor M1S not only has to feed this current source I1, but also this other current source I1. Because this transistor is now turned off. Now this has to supply the current for both of them. So what will happen is this node Vx is no longer going to faithfully represent your common mode voltage. Because when you have very large output swings, you are basically going to, the output is no longer actually tracking your output. It is no longer going to track your the common mode voltage. Okay. Now there is also one more problem, that it provides a limit on the output swing and other things, right? Or in other, basically this is what it is, that it provides a limit on the output swing. The other thing is it needs a minimum of what? VGS plus the voltage across the current source. So the output common mode voltage itself, a minimum voltage is required for this whole thing to basically work. All right. So, but many cases, if especially if you are using a telescopic cascode and all, that problem will basically be solved. So the first problem is that you have an V out CM with offset, right? And the other one is also basically that, just a minute. So the other problem is that for large output swings, the Vx that you get is no longer going to track your output common mode voltage. Okay. So that brings us to one more method of doing it, which is by using transistors in triode. Now, basically what this method does is that you take these two output terminals, which is Vout P and let's say Vout M, and you give it to two transistors where you are shorting the drain node. Okay. Now, what happens in this particular case? Let's say this is also called as Vx. Now, what happens if this node is going up and this node is going down, right? So this will have an extra current and this will have lesser amount of current. I mean, you'll have Gm delta V here and minus Gm delta V here. And because you're shorting the two drains, right, the current will basically circulate within itself. Okay. And as a result, this node X is going to react only to differential mode, only to common mode signals. And especially since this is in deep triode, if you bias it in such a way that it is, or if you size these transistors in such a way and bias them in such a way that it is in deep triode region, basically what you can think of is that there is a variable resistor here, another variable resistor here, and you have connected both of them in parallel. So when you have differential signal, the extra resistance that you get on one side is compensated by the extra resistance, the reduced resistance on the other side, right? So if both of them are in, so basically it's not so much as the Gm delta V. That is one way to understand it. Like if you talk about the transconductance, another way to look at it is if you think of it as just basically being a voltage controlled resistor if they are in deep triode. Okay. Now this gives us an effective resistance which is dependent on basically it is dependent on common mode voltage. Okay. But again, the same kind of a similar problem happens here when you have a large output swing for your op amp, right? Now what can happen is that when your input goes quite low, one of the transistors can go into saturation, right? You want both of them ideally to be in the deep triode region, but when you have large output swings, it is basically one can go into saturation and the other will remain in triode. So you don't have that cancellation effect happening any longer, right? If both are in deep triode, then one resistance increases, another resistance decreases, and the effective conductance remains the same. But whereas when you have large output swings, that cancellation of differential signals does not happen, and Vx becomes dependent on differential Vout. And secondly, there is one more problem that it basically needs at least VGS to operate. It needs to be at least above threshold voltage, right? So which means that there is a output swing restriction and output common mode restriction when you try to put these types of circuits in order to measure your common mode. Okay. So these are all different problems which are there, but these are all different circuits. So some of them are used in certain contexts, depending on what context is basically going to work out for that particular, which circuit will work for which context. Okay. All right. So now we have seen three different mechanisms and each of them has its own advantage and disadvantage for basically sensing. Now, how do you do correction? Now, how do you do common mode correction? Now, first of all, the simplest way of doing common mode feedback, especially in 5 transistor OTS, especially when you talk about deep submicron transistors or deep submicron processors, where the output impedance itself is not so very large. Okay. a simple CMFB, which is actually quite widely used, is basically like this. Okay. So what you're doing here is that you take these two resistors, R and R, this common point, you just connect it to the gate of M3 and M4. Now what happens in this particular circuit? We note that this node X, Vx reacts only to common mode signal, only to output common mode voltage, right? So this is given to directly to the PMOS transistor. So let us try to think through this and see if this particular scheme basically will work or not. Okay. So what did we say earlier? That if your IP is greater than IN, right? Your PMOS current is greater than your NMOS current. Now that will flow through this output impedance. So if IP is greater than IN, you'll have V out common mode increasing, right? Suppose the V out common mode is increasing, that is both sides the voltage is increasing, which means that this Vx will also increase. Now when Vx increases, what is it doing to the PMOS transistor? Basically the VSG is reducing because the other terminal is VDD and you are increasing the gate voltage and therefore the source to gate voltage reduces. Now a reducing source to gate voltage means that your PMOS current is now going to drop, which basically means that you are fixing the problem, whatever problem was there. On the other hand, if let us say the PMOS current is lesser than the NMOS current, now what will happen is the output common mode voltage will go down and as a result the gate voltage of PMOS will also go down, and as the gate voltage of PMOS goes down your source to gate voltage increases and therefore your PMOS current increases. So this is a very simple common mode feedback loop and this is quite widely used, especially when you have only this kind of a simple 5 transistor OTA, and especially when you have deep micron transistors where the output impedance is also not very high. Okay, so simple way to correct CMFP. All right, to do CMFP. Now let us look at one more way of doing it. So let us look at this other way. So maybe let us take the example of a folded cascode. Okay, so in a folded cascode, what do you have? You basically have, you know, a lot of transistors. Now, in this case, let us say we have a NMOS input pair. Right? And it is connected something like this. All right. Now, this is our V out. Let's call it as V out M, V out P. Right? And this is basically, now we need to sense this. Of course, you can sense it by using a resistive divider also. But again, because this is a folded cascode, this can basically backfire, right? So one way to do it is, let us say, I mean, let me give you one way to first do it, and then I will look at the other ways of sensing. So if you put a resistive divider here, right? Okay, and you take this output voltage. Now this output voltage is basically going to be the common mode voltage of your this thing. Now which one can you correct here? What are the different transistors which you can correct here? So basically there are 3 places where you can go and correct. One is that you can correct, let me call this, let me quickly write down the names. This is M1, M2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay. Now what you can do is that first and foremost, you can correct this NMOS current source. Okay, so that is to say, if your NMOS current source, I mean, there is some mismatch between PMOS and NMOS current, you can go and correct the NMOS current source here, or you can go and correct the PMOS current source here, or you can also go and correct the tail current source of your input pair. Okay. Let's call it M11, right? So the correction can happen to either the PMOS current source or the NMOS current source or the tail current source of your folded cascode. Now, how do you correct it? We put one more op amp, okay, and you give a reference common mode voltage. Okay. Now, what it will do is that it is going to measure this node X is going to measure the Vout common mode, and that Vout common mode is compared with the reference common mode that you want. For example, if it is a 1.8 volt supply system and you want your common mode voltage to be at, let us say, 1 volt, right? So you can give your Vref common mode to be 1 volt, and this is a single-ended op amp. So basically, this does not need any common mode feedback. This is fine. Now you can take this op amp and go and connect it to the gate of this NMOS current source. Now, what should be the polarity of the NMOS current source here? I mean, what should be the polarity of the op amp here? So let's try to see. So if suppose your Vout common mode is increasing, basically it means that your IP is greater than IN. In other words, if this is increasing, your NMOS current has to increase. Now, how will your NMOS current increase? If its gate voltage increases, right? So in other words, if your output common mode voltage is increasing, you need to go and increase the gate voltage of your M3 and M4 transistors, right? So which means that this is the in phase terminal and this is the inverting terminal. All right. Now the same thing if you were to connect it to, let us say, the PMOS current source or to the other tail current source, you have to kind of work it out and then you can do. So this is another very commonly used way of doing a common mode feedback. So basically you sense it, you compare it with the reference, and you use another op amp to drive any one of your current sources, right? I have shown here only for correcting the NMOS transistors M3 and M4. The same thing can be used to correct M11, I mean, same way, or you can also use it to correct the PMOS current source. All right. So this is another way to do the correction. Now, this sensing, the sensing of these two signals, I mean, the sensing of the output common mode, you can even use one of the other methodologies. Okay. You can use one of the other methodologies to correct, I mean, sense the thing instead of using a resistive divider. All right. Now let us see another way to correct common mode feedback, do common mode feedback. Now this is also possible. Okay. Now let me give you a. Let us take the example of a telescopic cascode. All right. Now what we do for telescopic cascode is also applicable for just a minute. I need to draw it a little lower. Now the same thing can be used even for a folded cascode. I mean, in the in a very similar way. Okay. So this is a telescopic cascode. Now what you do is, let's say this is your axial supply VDD. Okay. Now the way this common mode feedback is done is that you put two wide transistors which are expected to be in the triode region, and you connect them like this. Okay. Now, a similar kind of thing can be done on the NMOS side also, especially in the case of a cascode. You can do this either at the PMOS side or you can even do it in the NMOS side. Okay, the same kind of a thing can be done on both sides. In this case, because you have an NMOS input pair and you have a tail current source, you basically do this correction in the top side. Now, basically, what is this going to do? Now, this is the third method of sensing that I talked about, right? So here I use the example of a pair of NMOS transistors which are in deep triode. Here in this example, I have used a pair of PMOS devices which are in deep triode. So these two devices are in deep triode and they act as variable resistor. Now, if the output common mode voltage increases, okay, basically what are you doing? You're kind of reducing the source to gate voltage, which means that the resistance will increase. The resistance R effective is basically going to increase. Now, by increasing it, what will happen? Because there is a DC current flowing through this one, this node voltage will drop down and that will cause the overall common mode voltage to basically come down. So, in other words, what you are doing is that you are reducing the source voltage of this transistor. So, if this is 1, 2, 3, 4, 5, 6, 7, and 8, you are basically controlling the source voltage of your transistors 7 and 8, right? So by increasing the, or rather reducing the source voltage of 7 and 8, you are crunching the current of, you are reducing the current of the PMOS side. And as a result, what will happen is that the output common mode voltage will go down and vice versa, right? So this has to be a little carefully designed. And of course, the other problem that I talked about when you have very large swings, you know, I mean, it is a very good possibility that, you know, this transistors 9 and 10 go out of saturation. Go into saturation. One of them can go into saturation and that will cause problems. But if you're not expecting very large swings, this is a very good way to do common mode feedback. And the advantage of this method is that you're not putting resistors like this and you're not touching the differential gain of your OTA. Okay, so this is another way to do common mode feedback. In fact, you can do similar kind of a common mode feedback to in the folded cascade also. If you look at the textbook, you will see some different versions of it where you kind of take, you know, output these two things and go and you know put underneath, right? You put this and connect it underneath the tail current source. So with that, you are basically going to connect. So that is another way. I mean, basically what you do in the folded cascade, right? So you have your differential pair and then you have your transistor M11, right? This is M1, M2. Now what you do is you put two transistors underneath this, right? Let's call it M12 and M13. And this is connected to, let's say, Vout P and Vout M. Now what will happen is basically that it is in fact putting this with the variable resistor, M11 with a variable resistor in its source. And therefore, if let us say you are generating this current, I mean, this from some kind of a current source, VB, right? What you are basically doing here is that you are changing the source voltage and therefore thereby controlling the current through your differential pair. Now, of course, controlling the current through a differential pair will result in slight changes in gain and so on, but then that is still okay. So these are the different ways by which you can do common mode feedback, right? Now, lastly, let me just conclude with this. So when you have a two-stage op-amp, right? So where will you control? So there are different ways by which it can be controlled. Okay. So first way is basically to say, sense the final output common mode and correct the output current source. Okay. So that is to say, when you have a two-stage OTA, right? So you can basically, there is the final V out P and V out M. Now you sense the output common mode voltage, maybe using a resistive divider or something. And then you can go and control. Let us say the first option is to go and control these two current sources. This is the first option, right? Now the second option is basically to go and control the tail current source of your first stage. Okay, so you sense the output common mode voltage and go and correct the current source of your first stage. That is also possible. Now you can also go and correct the PMOS bias of your first stage as well. Measure the output common mode voltage of your second stage, go and correct the voltage on the first stage. So basically here again you'll have an op amp. So you have to put the appropriate terminal. So this will be the VREF common mode. This becomes the V out common mode, right? So you take this error amplifier, go and either correct at node 1, which is basically the NMOS current source of the output stage, or you can go and correct the tail current source of your first stage, or you can go and correct the PMOS of your first stage. Okay. Or there is also another option. So basically, this is output current source. Secondly, sense the output common mode and correct the tail current source. Or thirdly, you can go and correct the PMOS current source. All right. And there is also one more thing, basically the last method, which is basically to have a separate common mode feedback for first stage and for second stage. So that is to say, you can go and put a resistive feedback. Maybe you can put a resistive feedback here, right? This is only for the first stage. And then you take these two things and you put resistive feedback for the second stage. So in the second stage, what is the thing? So basically you will have something like this, right? You take a resistive divider and control the NMOS current source. So this is another way to basically do. So you have two separate common mode feedback loops for both the input side and the output side. Or you can have one common mode feedback loop with the particular fashion. For example, the first stage is a telescopic cascode. You can do CMFB in a certain way for the telescopic cascode, like probably one of the previous ways that we saw. And the second stage being a common source, that can be done in a slightly different way. And especially for two-stage OTAs, when you are doing common mode feedback, because there are multiple poles in this particular thing. So for example, if you are sensing the output and controlling the first stage current source and so on, now there can be multiple poles in that common mode loop, and that can result in common mode instability, which means that your op amp will go into common mode instability. That is, both V out P and V out M both will go up and down. Okay, it will not be a differential signal. Both will go up and down. In that case, you have to provide compensation for the common mode feedback loop. So which is why typically what will happen is that people will put a large capacitance. Okay, let's call it C1. So people will put a large capacitance at the output of this correction op amp, and by doing this correction, doing compensation for this correction op amp and reducing the bandwidth of this, you will make sure that your system is stable. Otherwise, there will be common mode instability also. Okay. So those of you who are doing fully differential OTA as your project for this particular course, you need to implement your common mode feedback as well. And this op amp which is you are using for common mode feedback can be a very simple 5 transistor OTA. Okay. So with this, I'll conclude the class now. Please do let me know if you have some time in the afternoon. Let me know by, let us say, 2 o'clock this afternoon. Okay. So if you say that you are not available, then I will just do a recording and put, or else those of you who are available can join at probably, let us say, 4:15. 4:15 to 5 o'clock, I'll conduct a design session, and whoever is available can join. The others can, watch it online. Okay. So thanks everyone. Have a nice day.
Thank you, sir.